Hello and welcome to this lecture. In this lecture, I will be showing you how to simulate a crude oil preheat train using Aspen Hysys. Now, a crude oil preheat train is just a network of heat exchangers that actually help to recover heat and then provide heat for the feed stream to the crude oil refining process, right? So in this tutorial, I will just be showing you how to simulate a basic crude oil preheat train, and this is actually a continuation of our series, the oil and gas simulations in Aspen Hysys. So in the previous videos, we treated how to specify crude oil streams using the oil manager and the petroleum assays, right? So this is actually a continuation of those particular tutorials. So if you don't know how to create crude oil streams in Aspen Hysys, I would suggest you actually check out those videos from the playlist, right? So for this particular tutorial, we would actually be simulating this problem, right? So let's get ahead with that. So we start by creating our crude oil feed stream. Now let's check the problem statement. So it says a crude oil stream at 15 degrees Celsius, 1000 kilopascal, and flow rate of 6 times 10 raised to power k 6 times 10 raised to power 5 kg per hour is mixed with a stream of water at 15 degrees Celsius, 1000 kilopascal, and 21,600 kilogram per hour using a mixer. The outlet from the mixer is then heated to 65 degrees Celsius through a heater. Pressure drop is 50 kilopascal. Then the heater is fed to the tube side of a shell and tube heat exchanger where it is heated using a shell inlet stream having the same composition as the crude feed stream and enters the shell of the heat exchanger at 180 degrees Celsius, 200 kilopascal, and a flow rate of 175 meter cube per hour. So for this particular simulation, I'm making use of the Bonnie light. So I'm making use of Bonnie light. Yes. So Bonnie light from the petroleum assay. You have Bonnie light. So I've already made my selections. So these are the details. These are the cut yields. Then let me see. Okay. So you have the curve for this particular the distillation curve, right? So you have it here. So basically, I just selected the Bonnie light from the petroleum assays. Like I said earlier, if you don't understand how to create crude oil streams, kindly check the playlist under the oil and gas simulations. You would see how to specify crude oil feed streams in Aspen Hysys. So let's quickly go over to what we have in this particular tutorial. So we require a mixer and then a heater. Yes. So a mixer, this is a mixer from the palette, from the model palette. You have this as the mixer. Then you have a heater as well. So we just specify inlet and outlet streams for this mixer. So can call the first one crude oil and then the second one is water. The crude oil and water are mixed using the mixer, right? So Let's shift this a little, and let me reduce the size. I'm reducing the size of my flow sheet environment, so I can reduce it further. Yes. So we can make specifications for the crude oil feed stream. So we have 15 degrees Celsius, 1000 kPa. Then we have our mass flow rate in kg per hour is 6 times 10 raised to power 5, right? So we just specify it as 6E5 kg per hour, right? So it says unknown compositions. So for that, we just click on petroleum assay and you click on attach existing, right? Based on the specifications made in the simulation basis manager, you click on attach existing. So this would help you specify. So this was the crude I chose in the petroleum assay, Bonny Light 2011. So I just select it, and then current status is assay attached and your stream is okay, right? So basically that's how to do this. Okay, so going back, then we can specify water as well. Water is also, I believe, is 15 degrees Celsius and 1000 kPa as well, right? Then for mass flow, we have 21,600, if I'm not mistaken, 21,600 kg per hour, 21,600. Then composition of water would be 1. Okay, let's see. Yeah, H2O composition is 1, right? So this is H2O. So we okay, and this particular stream is fully specified as well, right? So we have specified the first aspect of this model, which is to specify the mixer and the inlet streams. So next is to specify the heater. So back to the problem statement, it says the outlet from the mixer is then heated to 65 degrees Celsius through a heater. Pressure drop is 50 kilopascal. So we need an energy stream for your heater. Then heater outlet, let's just do let's use this as the heater outlet. Then the inlet is the outlet of the mixer. So we have unknown delta P. You go to your parameters and you specify. So we have 50 kilopascal. Then it says unknown duty. So for duty, we make use of temperature instead. Temperature is given in the problem statement as 65 degrees Celsius. 65 degrees Celsius. So we hit enter for that, and that has been solved. So we can continue with our model. So let's reduce the screen further so we can continue. Then we can bring this to the left a bit. Right. So the next thing to do is to specify the heat exchanger. So we have the heat outlet is fed to the tube side of a shell and tube heat exchanger, where it is heated using a shell inlet stream having the same composition as the crude feed stream and enters the shell of the heat exchanger at the following parameters, right? So let's get a heat exchanger. So for the heat exchanger, we have the shell and tube here, right? We have the shell and tube. Yeah. We also have a plate exchanger here as well, right? We are making use of the shell and tube. Okay, so tube side inlet is this. Um, and then we can name our tube side outlet. Then we can have this as shell inlet and then shell outlet as well, right? Shell outlet, right? Okay, so that's for that. Then let's go back and get more details about the inlet and the outlet for this particular heat exchanger. By the way, we can format or change icon. We can change the icon to this, which is a better representation of the heat exchanger. We can use this for our heat exchanger, so it specifies or displays it as a heat exchanger in a better manner. Okay, so going back to this, so we have details about the shell inlet stream. We have details about the shell inlet stream, and it also says the shell inlet stream has the same composition as the crude feed stream, right? Also, pressure drop for tube and shell sides. For tube side is 35, for shell side is 5, right? Pressure drop for tube side is 35, so we can quickly specify those. So we have tube side pressure drop. So we go to parameters. We have tube side as 35 and we have shell side as 5. So let's confirm that. So um tube is 35 and shell is 5 kPa. So we are good with that. Tube is 35, shell is 5. So we can now specify the shell inlet. So for shell inlet, we have uh, volume as 175 meter cube per hour, right? 175. Then pressure is about 200 kilopascal. Then temperature is about 175 degrees, okay, 180 degrees Celsius. So we have 180 degrees Celsius, right? So these are the properties and their values. Then composition is the same as that of crude, right? So for that, we are going to use this function here, define from stream. So we are trying to define the composition of the shell inlet from the crude oil stream, right? So we are defining from a different stream, right? This occurs when streams have similar parameters, right? In this case, the similar parameter is composition, right? Composition is the same, so we can uncheck temperature because we specify temperature and pressure. We can uncheck them. Available streams are all the streams in the flow sheet, right? All the streams in the flow sheet. But in our case, we want to make use of the composition of crude oil. The composition of crude oil. So crude oil is selected. If you want to use another stream, you can actually select it. But in this case, our target stream is crude oil and it's already selected. We deselect temperature and pressure because they were specified. We deselect all of this. Yep. We also deselect. Can we deselect flow? Yes, we deselect flow because we specified volumetric flow rate, right? Volumetric flow rate was deselected. So all we will be selecting is composition. So composition, we select composition and we click on OK. OK. So once you specify your composition, it completes the stream and the stream solves, right? So we have been able to solve this and this has been specified, right? So for the heat exchanger, uh, the heat exchanger is still underspecified. So we go back to the problem statement and see what we can gather from it. So from the question, we have the heat exchanger specifications. So we have use simple weighted model and then shell side outlet temperature is 95 degrees Celsius, right? So basically, these are the parameters we need to solve this particular heat exchanger. Okay, so shell outlet is 95, but before I specify that, let's go back. So, okay, so it asks for simple weighted, so we specify as simple weighted. So for simple weighted, then we go and specify the shell outlet, which is 95 degrees Celsius. So we can still confirm that the shell side outlet is 95 degrees Celsius. So this is shell out, so 95 degrees, and we are good, right? So we are good with our heat exchanger. We are good with our heat exchanger. We can continue with our modeling. So let's go. Okay, so we can go back to the problem statement and scroll up a little bit. So it says the tube outlet from the heat exchanger is then sent to a desalter, which is simply modeled as a three-phase separator where desalted water, oil, and gas is separated. So we are going to be modeling that right now. So we have is modeled as a three-phase separator. So we bring out our three-phase separator and we specify it, or we place it on the flow sheet at any suitable place. Let me see. Okay, so for this, basically, desalter is an equipment that actually removes salt from crude, and it does that by the action of water. So water is added to separate um, salts from crude, right? So the salt would dissolve in the water, right? Salts would dissolve in the water. That's the salts present in the crude will dissolve in water. Then the water will be separated from oil and gas, right? That's basically how it works. So, and that's the reason why water was added to the crude oil initially, right? So it dissolves the salts present in the crude, and then that is separated from oil and gas, right? So you can we can specify this as gas, then this as oil, and then this as desalter water, right? Right. So basically, it just separates um the desalter just separates brine. Yeah, it's usually brine because it's a mixture of water and salt. So brine from oil and gas. That's basically what it does. So that's how it works. So we have the three streams fully specified. So we can continue with the model. So going back to the problem, let me see. Okay, so where oil and gas is separated, right? So just modeling a three-phase separator, no other specifications was given about that. So we move on. Then you have the oil stream from the desalter is heated to 175 degrees Celsius and then sent to a pre-flash to reduce light components in the feed, right? So we are sending to another heater. So we need a heater for the oil, we need a heater, and then we also need a pre-flash. In this case, the pre-flash is a two-phase separator. So we just do, so let's go back. So we have our pre-flash, then we can specify this one, which is the heater. So the feed to the heater is oil, then we can just say hot oil as the outlet, then an energy stream is required. So we specify our duty, or in this case we are specifying temperature. We specify temperature as 175 degrees. So we have 175 degrees Celsius, and then we can specify the pressure drop. Pressure drop is 375 kPa, 375 kilopascal. So this actually solves the model, right? So you can either specify outlet pressure or you specify your pressure drop, right? Depending on the data you have. So we are going forward. So we are sending hot oil into the pre-flash, right? So we send this into the pre-flash. So we have hot oil as the feed to the pre-flash. So that should actually solve the pre-flash as well. So yeah, so it separates the vapor present in the liquid from the liquid, right? That's basically what it does. So and all of these are part of our preheat train. So we still go back to the problem statement. So oil stream from the desalter is heated to a heater and then sent to the pre-flash to reduce the light components in the feed. So the light components are actually the vapor stream, right? Next, liquid product from the separator is then heated to 400 degrees Celsius inside the heater before it enters the atmospheric distillation column, right? So basically, that would actually end this particular preheat train. Yes. So we model a heater, another heater that actually heats the liquid from the pre-flash to 400 degrees Celsius. For this one, you can decide to change icon if you want. So let's say we use this guy for this. So our inlet stream is liquid. We need an energy stream, and then let's say we call this ATM feed, which is the feed to the atmospheric distillation column. And then we go back for our parameters. So we have 400 degrees Celsius, which is the outlet temperature, 400 degrees Celsius, and then about 250 kPa, if I am not mistaken. Yeah, 250 kPa. So we have 250 kPa here, 50 kPa, right? So that actually solves that. So we can change the direction of this guy, right? So at my top, you have flip horizontal. Let me see. Okay. Okay, I would just change that. I want to do it in such a way that it's actually in the direction. Okay, so I think I can move this guy forward. That's the outlet stream. I can move it forward. Okay. Let me see. Let's see if we can make this better. Okay, yeah, so we've been able to do it. Um, Still trying to see how best I can turn this. Let me try turning only the. Okay, let me see. Nope, it's not. It's not going the way I would have. Okay, let's see. It's not going the way I would have wanted it to go. Um, okay, but I'm guessing we can make use of this. I'm trying to see if there's a way I can turn this properly. Okay, but it's still that way. Okay, based on that, we would have to actually let it be like this. All right. So basically, we've been able to model um the crude oil preheat train. Okay, I think I would change to this instead. I think I prefer this. Right. Yep. So you can do a lot of things with your model to just make it look better, right? And most of these have been taught in previous lectures. You can check the playlists, Aspen Hysys hacks. I believe there is a lot you can learn from there. You can also increase the size of an icon if you want. Yeah, that's it. So you just increase it a little bit. Yeah. So it increases in size. Yeah. So we can start to actually answer the questions that were asked in the problem. So the first question says the vapor fraction of the product stream before entering the atmospheric column. Now this is asking for the vapor fraction of the stream that comes out of this particular heater that heats the liquid product to 400 degrees Celsius. So the outlet stream of that particular heater, we are request it is the problem statement is requesting for the vapor fraction of this, right? So the vapor fraction, we have 0.9267, right? That's the vapor fraction, 0.9267. Then for the next question, we have minimum approach. Okay, the minimum approach, and then okay, let's answer that first. For minimum approach, you are talking about the heat exchanger. Uh, we already have an extensive video about heat exchangers. You can check this playlist, simulations with Aspen Hysys, or you can check Aspen Hysys for process engineers. You'll see the detailed tutorial on heat exchangers, right? Okay, for the minimum approach, you can check it from the performance tab, right? So you can see the overall performance of your heat exchanger. So from here, we have a minimum approach of 30 degrees Celsius, right? 30 degrees Celsius. Then for the last question, we have the vapor molar flow rate from the pre-flash. Vapor molar flow rate from the pre-flash. So this is our pre-flash. So the vapor molar flow rate is 109.3, right? Vapor molar flow rate, right? So this is our vapor stream, and this is the molar flow rate, right? So it's actually 109.3, right? This is your vapor molar flow rate, right? So with this, we have come to the end of this particular tutorial, which is a part of a series, the oil and gas modeling in Aspen Hysys. So in the next tutorial, we would actually be simulating the atmospheric distillation column, which would actually continue this particular model, right? So this um, particular stream right here would be the feed to that particular tutorial, right? So if you have any questions based on what has been taught in this particular tutorial, you can let me know in the comments. Like this video and share with your friends. Then if this is your first time, kindly subscribe to this particular channel to get more notifications about subsequent videos on process design. Thank you for joining me in this particular tutorial. Do have a good day.